We will we will start the lecture in, let's say, 5 minutes. We can wait for 5 minutes and then we can start. So let's start with today's class. So this is week number 10, whereby we are covering the doubts related to the course content of heat transfer NPTEL course. So in this week, we covered the properties of black body, surface adsorption, Kirchhoff's law, radiation exchange and view factor, and then saw a few examples of view factor. So today we will start with solving the numericals related to those. Basically, the numericals related to radiation that involves the black body radiations, Kirchhoff's law, or surface adsorption. So in previous class, we had covered this fundamentals of radiation. So one thing we derived was this radiation intensity. So radiation intensity is dependent on the wavelength theta and phi, where theta and phi are the, you can say, directional component or the angle at which the radiation is incident or radiates. So on the basis of that, we derived this formula for this radiation intensity. Then we derive this emissive power of the surface by using this formula, whereby for a particular wavelength, we integrate it across all the phi as well as this theta in order to find the overall emissive power of the body. Similarly, in order to find the total emissive power across all the wavelength, we can simply integrate it across all the wavelength. So this gives us a formula that is the total emissive power is pi times of IE, where IE, as we defined, was this radiation intensity. So if we have to find the radiation intensity, we can simply divide the total emissive power by pi. Then same formula we derived for this irradiation. Then we started with this black body. So in previous week, we had the course had discussed about this Planck's distribution of spectral intensity, whereby this graph shows that the spectral emissive power versus wavelength will peak at some certain point, and that the formula for spectral distribution is given by these correlations. So in order to find this peak point, what we can do is we can just differentiate this equation with respect to lambda, and it will give us the correlation between the lambda maximum and T. So that is basically Wien's displacement law. So this graph basically shows that the spectral emissive power is dependent on the wavelength as well as temperature. So as we move the temperature from 50 to 1500, we can see that the maximum emissive power will increase, and the wavelength corresponding to that will decrease. That is how we come across this correlation, that is the maximum wavelength will be inversely proportional to the temperature. Then yes, we can derive this Stefan-Boltzmann law for a black body that states that the total emissive power is equal to sigma times of T raised to 4. Then if we have to find the band emission, that is the fraction of energy emitted until a particular wavelength. So for example, if I have to find from 0.1 to 4 micrometer wavelength, then we can straight away integrate it within this range. So that will give us the band emission, and on the basis of that, we can derive this fraction f of 0 to lambda, that basically states that the fraction of energy emitted by that body in the range of 0 to lambda upon the total energy emitted across all the wavelengths. So this f of 0 to lambda will give us this ratio, and it will be basically the function of wavelength as well as the temperature. So eventually we can derive all these equations. Then again, see, we studied that the radiation intensity is dependent on lambda, theta, phi, and then we also derived that this E lambda will also be dependent on this lambda as well as its temperature. That is what is shown. So this I lambda will dependent on directional dependence. That is, it will be dependent on the angle at which the radiation falls. So that is given by the theta. And whereas this E lambda, we saw that it was dependent on lambda and T. So then we can derive this formula for hemispherical emissivity. So this basically shows the ratio of the energy emitted for a particular temperature if we consider all this lambda, phi, and theta with respect to that of black body, the ratio with respect to that of black body, that will give us the total hemispherical emissivity. Whereas in case of spectral hemispherical emissivity, we'll find this for a particular wavelength. So that is a wavelength, and temperature will be fixed, and then we will just integrate that radiation intensity. The radiation incident on an angle of theta on the other body with respect to pi by 2 and 2 by pi. So since we are considering this hemisphere emissivity as shown over here, so if we are considering this hemisphere, that is why we are just integrating it across 0 to pi by 2. Then we can derive this spectral absorptivity, reflectivity, and transmittivity. And then for a semi-transparent medium, we can write this equation, and for an opaque medium, we can write that alpha plus rho, that is absorptivity plus reflectivity, will be equal to 1. And in case of semi-transparent medium, we will be also having this transmittivity. Then we saw this Kirchhoff's law that is used for the objects which are not perfectly black body. So for those, we can just write the energy in terms of, by considering them as a semi-transparent medium, in terms of this black body radiation. That is EB, by defining this for this emissivity, reflectivity, all those terms. So this basically states that the emissive power of a gray body or any object is proportional to is equal to this emissivity into the black body, where emissivity is the emissivity of the object for which, or of the gray medium for which we need to find the total power. Then we saw all the spectral equivalence for this emissivity as well as absorptivity. This is nothing but we just have to integrate it across all the angles. Similarly, if we want to find the emissivity, it as shown by Kirchhoff's law, it is nothing but the ratio of the emissive power of the gray medium upon the total emissive power of the black body. And that is what is shown over here. Then there is this radiation exchange between surfaces. So whereby we also take into account the geometry of the surfaces. Earlier, we were only taking into account the temperature, wavelength, and visible directional parameters of both the bodies under which radiation is occurring. But if it is occurring between two surfaces, then we also take the geometry into account, and for that, we derive this view factor. That is nothing but the fraction of radiation incident from I to j. But this will be more clear when we solve the numericals of this part next week. So these are the formulas related to the radiation of radiation that leaves a surface I and is incident on j. So that is given by this formula I times of cos theta I upon dAi cos theta j dAj upon r square. So this term is given by this angle d omega j I, whereby theta I, you can see, is the angle from which the radiation occurs. So if you consider that radiation is occurring in this direction, then this is the theta I, and the angle at which the radiation is incident, the angle that it makes to the perpendicular of the surface. So if I take a normal to the surface or perpendicular to the surface, and the angle made by the radiation is theta I, whereas on the object on which it is reflected, it becomes theta j. So this theta and theta j we need to take into account. Rest all dAj is the area of the first object, dAj. dAi is the area of the first object, dAj is the area of the second object, r is the distance between these two objects. So this rule we will see in next class. So that was all for the theory of the today's class. So now we can start solving few numericals. If you have any doubt, you can unmute yourself and ask. So let's start with the first question. So the question is as a small surface of area A1 10 raised to minus 3 meters square is known to emit diffusely, and from the measurements the total intensity associated with emission in the normal direction is IN equal to 7000 watt per meter square steradian. Radiation emitted from the surface is intercepted by three other surfaces of area A2, A3, A4 equal to 10 raised to minus 3 meters square, which are 0.5 meter from A1 and are oriented as shown. What is the irradiation at surfaces A2, A3, and A4 due to emission from A1? So yes, we have been given that we have this small surface A1. It emits diffusely, that is radiation is occurring from this A1, and it is incident on three surfaces A2, A3, A4 at the angles shown in the figure. And for this, we have to find the irradiation at the surfaces A2, A3, and A4. So basically, we have to find this value of Gj, for which we have been already given the formula, whereby I1 is nothing but the radiation intensity. Theta j is the angle made by the radiation with respect to the perpendicular of the surfaces. So basically, if I'm considering this A4, then the angle made by this A4 and the radiation in this direction, that is 45 degree, is theta j. Then omega 1 to j, we derived it in the previous class. So if you remember, this was derived as, we derived as d omega was d an upon r square. So this will eventually come as omega 1 to j is equal to a1 cos theta 1 upon r square. So in this case, it will be a4 cos theta 4. A4 is this area. Cos theta 4 will be the angle made by this perpendicular with this radiation. So it will be nothing but 0 degrees. So cos of theta will be over here, the theta 4 will be 0. So we can just replace it over here and then find the value of g of j. Alternatively, you can also use this formula, whereby q1 of j is nothing but I times cos theta ij omega j minus 1 upon a of j. So you can use any formula, whichever formula you want. So let's solve this question. So we have been given the formulas as one thing, that is what we can say, that we know the formula for the irradiation. It is g of j will be dependent on the radiation intensity I1, the angle at which the radiation leaves, and then this steradian parameter whereby it shows the angle and area at which the radiation is incident over here. So we can use this formula in order to find G2, G3, G4. So let's find that. So let's just start with this A3. So for A3, you can write this G3 is equal to I1. So the angle made by this perpendicular of A3 with this radiation will be 0 degree. So it will be I3 cos of 0 degree into omega 1, 2, 3. That is omega 1, 2, 3. So this we saw as A1, basically this area A1, then cos of angle made over here. So that is around 0 degrees upon the distance between these two square. So that is 0.5 square. Cos of 0 over here is also 0 degrees. So this will be I1 into A1 upon 0.25. So I1 is 7,000. A1 is 10 raised to minus 3 upon 0.25. So this will be 4 times of 7, that is equal to 28. Since it is radiation, so it will be watt per meter square. So the value of G3 is 28 watt per meter square. Similarly, now let us consider this A2. So for G2, it will become I1. So now we have to consider this angle, cos of 60 degree, A1. Now we have over here, we have to consider this angle made by the perpendicular, that is 30 degree. Upon this R square will remain same, that is 0.25. So this will become 7 into root of 3 by 2, 1 by 2 into 4 will get cancelled. So this will come around 7 into root of 3 plus 12.12. So G2 is 12.12 watt per meter square. So fine. Now let's take this case for A4. Similarly, for A4, we can write G4 as I1, that is 7,000, cos of this angle 45, area is 10 raised to minus 3, and then again cos of this angle, so over here it is 0. So cos of 0 will be 1 upon R square, that is 0.25. So this will become 28 into 1 upon root 2. So this will come around 19.8 watt per meter square. So this is how we find the radiation given the following geometry by using these formulas. So let's take a look on the provided solution. So the radiation was calculated using this formula where omega 1 to j is given by this formula. And then we find this J2, J3 for values. Now let's take a look on the second question. This question is again a little bit similar to the previous question. So over here we have been given that a furnace with an aperture of 20 mm, that is with area of AF, diameter. So for 20 mm, the object that we have been given is AF, the emissive power of 3.72 into 10 raised to 5 watt per meter square, that is E, is used to calibrate heat flux gauge having a sensitive area of 1.6 into 10 raised to minus 5 meter square, that is AD. At what distance measured along the normal from the aperture should the gauge be positioned to receive the irradiation of 1000 watt per meter square, whereby we have been given that theta F is equal to theta D is equal to theta 0 degree. Then we have been straight away given this formula for the irradiation over here for this case. So very similar formula we saw in the previous case also. So this formula, if you want to derive, you can just derive it as, so we saw that G is Q from F to D upon the area of this detector. So it will be A to D. Now this formula, we know that it will be dependent on the intensity IE upon this area AF cos of this angle theta F and then omega D2F. Now IE, we saw in the previous notes that it is nothing but the ratio of this total emissive power upon pi into AF cos of theta F into omega D2F. We can write this as the area of the detector AD cos of theta D upon the distance square, that is L square. So this is given by G. So this is what has been, I think, written over here, E by pi AF cos theta F. So omega D2F is given by this formula over here. Okay, and then we have to also divide this by AD, so that will come over here. On AD. So these both of these are same formula, so we have just expanded this term over here. So from this we can find this value of length that has been asked. So let's see the solution again. So yes, we derived this formula, and from that we can find the value of length that has been asked as. So length will be E upon pi times G into AF, and then this AD will get cancelled out into cos of theta F cos of theta D. Yes, that's all. So this will be square root. So now we can just put all those values over here and then find the value of length. So that is, we have been given L as The emissive power is given by 3.17 to 10 raised to 5 watt per meter square. Upon pi G is 1000. The area of this will be pi times of 0.02 whole square, pi r square. Then theta f and theta d will be 0 because both of them are at the same angle. So cos of theta f and theta d are 0, so their cos's will be 1 into 1 whole raised to 1 by 2. So this you can calculate. I will get cancelled out. Yes, it will correct. It will be pi by 4 d square. It will be pi by 4 d square. So this should. So this will come around square root of 0.0372. So it will be around 0.1928 meter. So that is 192.8 mm. So the distance between the furnace aperture as well as detector should be 192.8 mm. So that was the solution. We'll take a look on the final answer. It is around 192.87 mm. So now let's move on to the next question. So the questions related to radiations are fairly straightforward, whereby we don't have to do much calculations. So just do them. We can try solving this question and then we can discuss the solution methodology. Okay, sorry for the delay. So we can try solving this question. So in this question we have been given, consider a metallic surface with the measurements of spectral, hemispherical emissivity yield, a spectral distribution which may be approximated as follows. So over here we have been given spectral distribution, that is nothing but basically EB, this emissive power at different values of lambda, and not emissive power, this you can say emissivity at different values of lambda that we have been given, and then we have been asked to find this hemispherical emissivity for this given for this given whatever wavelength that we are talking about. And then we have been given this hint which states that for this given spectral distribution we can just break it in two parts. If in the first part the emissivity is 0.36, in the second part the emissivity is around 0.2, so we can just break the spectral distribution into two parts, from 0 to 2 micrometer, and then 2 micrometer to 4 micrometer, and then use this formula in order to find the total hemispherical emissivity. So using all this information, we have to find the total hemispherical emissivity at this 1750 Kelvin. That is what we have been asked to find. So this ratio, if you remember, this ratio is nothing but f of 0 to lambda. So over here, since it is going from 0 to 2, so this ratio we need to find for f of 0 to 2. Similarly, over here, we need to find the ratio of basically the band emission from the wavelength of 2 micrometer to 4 micrometer to that of the total oral black body radiation EB. So that value f of 0 to lambda is given in this table. So using this table and this plot, we have to find the hemispherical emissivity at 1750 Kelvin. So let's take a look on the solution methodology. So the first thing we have been given that we have to find the hemispherical emissivity at, let's just write it over here. We have to find this epsilon at temperature of 1750 Kelvin. So for this temperature and this wavelength, we need to find f of 0 to lambda. So, and then put it in these equations in order to find the total emissivity. So the total hemispherical emissivity will be epsilon 1 upon f of 0 to 2 micrometer plus epsilon 2 f of 2 to 4. So this f of 2 to 4, we can write it in terms of f1 of 0 to 2 plus epsilon 2 f of 0 to 4 minus f of 0 to 2. This is what we can write. So now we need to find f of 0 to 2 and f of 0 to 4, and then put the value over here in order to find this total hemispherical emissivity. So in order to find f of 0 to 2, we can see that we have been given the values in terms of lambda t. So we can first calculate the value of lambda t for this part. So over here, we can write this lambda t. So the maximum wavelength, lambda max t, in this range is 2 micrometer. So that will be 2 times of 1750 that is 3500. Lambda mt over here is this, and over here lambda t will be 4 into 1750, that will be twice of this, that is 7000. So for 3500, in order to find f of 0 to 2, we can just take the average of both of these terms. So that should give us, so the emissivity in this range is 0.36 into f of 0 to is nothing but average of both of these terms. So 0.27 plus 0.48 upon 2 plus epsilon 2, that is epsilon in this range, is I will be given something is around, you can read it from the chart that it is approximately equal to 0.2 into f of 0 to 4. 0 to 4 basically it means this range until 7000 this micrometer Kelvin, it will become this 0.808 minus f of 0 to 2. We can calculate that this from this term. So the average is 27 plus 0.48. This will come around 0.0866, yes, 0.36 into 0.375, 0.735, that's 0.0866. So this will come around 0.2216. So the total hemispherical emissivity at 1750 Kelvin, if we use the spectral distribution, is around 0.2216. So yes, that is what was asked in the question, and that is our final solution. So you can again take a look on the solution. So now let's move on to a question which is very similar to this one. So let's take a look on this question number 6. You can try reading it, and I will just. In the assignment, problem number 3. Okay, I'll just check it. Let me just see the question first. I have stopped sharing the screen. So you have doubt in this question number 3. Correct, na? So, okay, so you are not able to understand this figure. Let me just So see, in this question, we have been asked to find the spectral emissivity, correct? So the formula that we, I think, already saw over here. So if the spectral emissivity changes with wavelength, we can just integrate it with respect to the wavelength. That is what we saw in the previous question. Over here, what we have been given is that the spectral emissivity is changing with this and value theta, correct? And then in the question, we have been given that it is isotropic in phi direction. So basically phi remains constant. So although all those other parameters you can just treat it as constant, and the value of theta is the only value that is changing. So basically what you have been given is, so if you just, and if you can understand this diagram, so over here you can see if the angle goes from 0 to pi by 4. So basically, if you just consider 0 to pi by 4, then the emissivity for this case E theta is given as by this term 0.8. Okay, 0.8, and then you will be having some term over here cos theta and sin theta d theta 0 to pi by 4, and then for the second part you have been given pi by 4 to pi by 2, correct? And for pi by 4 to pi by 2, the emissivity is given by this 0.3, and over here we will be having cos theta and sin theta. So you can just take the summation of both of this term in order to find the spectral emissivity, and then in order to find the ratio, I think you have been asked to find the ratio of En upon Eh, so that you can calculate it. So basically at angle of 0 degree, the value is 0.8. That is, you need to divide 0.8 upon whatever value that is you are getting from this summation. That is the ratio you have been asked. The ratio of normal emissivity, or normal emissivity will occur when the angle is 0. That is 0.8 upon the hemispherical emissivity, is how we can, by using this graph. So basically, so first thing is over here it will be sin theta and cos theta. So you can consider, I think you can consider this example. So this d phi is given as constant. So ultimately from denominator, numerator, it should eventually get cancelled out. So this term will also eventually be equal to 1. And then you can just see it will become cos theta sin theta, integration of 0 to pi by 2 epsilon cos theta sin theta. But we don't have to, we haven't been given this 0 to pi by 2. We have to break it into two parts, 0 to pi by 4 and then pi by 4 to pi by 2. That is how we have to do, because the emissivity is changing with respect to the theta over here. So yes, you have to use this formula, but since phi is remaining constant, you can just treat that as constant. This d phi is constant. So eventually the numerator and denominator will get cancelled out. So you can just neglect this. What you can do is, see, in the question you have been asked to find the ratio of epsilon n upon epsilon h, correct? epsilon n upon epsilon h. Epsilon n occurs, epsilon n is nothing but a normal emissivity. Okay, normal emissivity occurs when the angle is 0 degree. So from this plot, if the angle is 0 degree, then the emissivity is 0.8. And if and then we have to find this epsilon h. Okay, so once you find the epsilon h, we can put the value over here, and the epsilon h will be nothing but you can just cancel this term. The denominator will also get cancelled out. So epsilon h will be eventually be 0 to pi by 2. Epsilon, that is a function of theta, cos of theta, sine of theta, d of theta. Now this e theta, I think it should get cancelled out. You can just work it around. See, if you take over here also, we will be having some parameter. Okay, if you take this normal. So that is how it should eventually get cancelled out. That I need to check. But the overall, you can derive this formula. The hemispherical emissivity will be this equation. I don't think I have the final formula over here. So yes, you can straight away use this formula, and you can use this formula. So, but this value of e theta you have to obtain from the graph. Yes, you need to multiply it by, I think you will need to multiply it by 2. Over here there will be 2. That I think it should come. I think we can just try integrating it 0 to pi by 2. That I need to figure it out. So I think it can come from this denominator also. If we integrate it can. We need to work out the math. So yes, you are correct. Over here there should be a factor of 2. Again, I can't share the exact solution or the exact methodology with you because this is a running assignment. But the solutions will be posted on the similar lines by next week. But that is why we are not allowed to discuss this current assignment questions, because we can't just discuss the solutions. Once you have the doubt in this question after the deadline has been over, then we are allowed to discuss the solutions. In Sir's note, I think he would have derived this formula. I don't think he has derived the formula, but you can get the solution by using this equation. Yes. Okay, so do you have any other doubt apart from this question? So I have a similar question to that, but so let's see this question number 8, which is again very similar to the question that has been asked in the assignment. But in the assignment, we have been given the graph, whereby over here I have just taken a straight away formula. So let's just first solve this question and then we can solve that question. Okay, so in this question, we have been given that the directional total emissivity of non-metallic materials may be approximated by this. So E theta we have been given as En upon cos of theta, where En is the normal emissivity. So what is the ratio of the total hemispherical emissivity for such materials to the normal emissivity? So if the total hemispherical emissivity is epsilon, then the normal hemisphere, so the ratio will be epsilon upon epsilon n. So this ratio we have been asked to find. Now this total hemispherical emissivity, as we were discussing, it is nothing but 2 times of 0 to pi by 2, since we are considering this hemisphere. Then this epsilon, that is a function of theta, into sine theta cos of theta d theta upon epsilon n. So this E theta, we have been given this formula, En upon cos of theta. So integration of 0 to pi by 2 En cos theta sine theta, again cos theta d theta upon epsilon n. This epsilon n is constant, so we can cancel. So the ratio will become 0 to pi by 2 cos square theta sine theta d theta. So if you integrate this term, I can use my calci to integrate it, or else you can also use this property. So if we are having this f of x raised to n into f dash of x integration of d theta, so this term, I think, is f of x. So this integration becomes f of x raised to n plus 1 upon n plus 1. So this integration will become, okay, over here we are having 2, so minus of 2 epsilon we cancelled out, cos cube theta upon 3 into pi by 2 plus 0. Cos of 0 by 2 by 3. So this ratio will come around 2 by 3. So yes, this question is the very similar to that asked. So you can just integrate it, cos square theta into sine theta d theta. You can either use your calci to integrate it, or this integration, we have this formula. So if we are having integration of some 0 to, let's say, a, f of x raised to n into f dash of x d of x. So this formula we can also write it as f of x raised to n plus 1 upon n plus 1. So this is the formula for integration. So over here, f of x is cos theta, and f dash of x is basically minus of integration of cos theta will be minus of sine theta. So that is why it is of the form of f of x raised to n into f dash of x. So that is how you can just integrate it. So it will become cos theta raised to n plus 1. That is n is basically 2. So n plus 1, that is cos theta raised to 3 cos cube theta upon n plus 1 is 3. And then we have to just apply the limit of pi by 2 to 0. So cos of pi by 2 is 0 and cos of 0 is 1. So it will come around 2 by 3. Okay. You can mute yourself. So yes, the same concept we have to use in the assignment question. So that is how I know this formula. So it is nothing but 2 times of integration of 0 to pi by 2 e theta sin theta d cos theta d theta, and this formula will come from that equation that we already saw from the previous. I don't know the derivation exact, but I know that it comes from that formula only. So now let's take a look on this question number 6. So in this question, we have been given that the spectral distribution of the radiation emitted by a diffuse surface may be approximated as shown in figure 1. What is the total emissive power? That is, we have been asked to find Y, we have asked to find E, and what is the total intensity of the radiation emitted in the normal direction at an angle of theta degree from the normal. That is IE. We have been given, we have been asked to find IE under the assumption of diffuse emission. Now, since we have been given diffuse emission over here, so this intensity of the radiation IE will not depend on theta. So it will be independent of this direction theta. So we can just neglect the last statement in this question, theta, that is theta equal to 30 degrees, that has been given. So the total emissive power will be only the function of the wavelength. So it will be nothing but integration of 0 to infinity E lambda upon d lambda. It won't depend on the angle since we have been given this diffuse emission. So now this E lambda, we can just read it from the plot and then integrate it, and then we will be having this total emissive power. And then in order to find the total intensity, you can just you can just take you can just divide it by pi. So yes, the total emissive power is nothing but integration across the entire wavelength spectrum d lambda. So you can just break it into this part. So from 0 to 5 it will be 0, so you can just neglect that. And from 5 to 10, integration from 5 to 10, 100 d lambda plus integration of 10 to 15, 200 d lambda plus integration of 15 to 20, 100 into d lambda. So this will be 500 plus 1000 plus 500. So total emissive power will come around 2000 watt per meter square. Now, in order to find the total intensity, we saw this formula in the notes. That is, so see over here we had written that the diffuse emitter is independent of the direction. That is, it is only dependent on lambda. That is why we just neglected the angle of 30 degree. And then the total emissive power we have been given is pi times of IE. And over here we have been asked to find this intensity of radiation IE. So we can just divide it by pi. So it will become IE will become E by pi. So it is 2000 upon 3.141. So it will come around 637 so watt per meter square per steradian angle. So that is our final answer. So you can take a look on the solution. So next I have this question, but this question has already been asked in the assignment. So I won't be solving this. Question number 8, we already saw. I think I have missed one question. This question here. So let's take a look on this last question of the day. So this is question number 5. So hereby we have been given that an electrically powered ring-shaped radiant heating element is maintained at a temperature of Th equal to 3000 Kelvin and is used in manufacturing process to heat a small part having a surface area EP is equal to 0.007 meters square. The surface of the heating element may be assumed to be black for theta 1 equal to 30 degree. That is, this angle is 30 degree and theta 2 is equal to 60 degree. So basically we have been given this angle that makes, so if this is the surface, the perpendicular to this, and this is the angle that we have been in 60 degree, and the length, the distance, basically this distance we have been given as 3 meter, the width as 30 mm. What then we have L equal to 3 meter, W equal to 30 mm. Then what is the rate at which the radiant energy emitted by the heater is incident on this part? So over here we have been given this heater, and it is emitting the energy on this small part, and then we have been asked to find the radiant energy, that is Q from heater to this part. That is what we have been asked to find. So let's take a look on the solution. So what we have been asked in this question is we have to find Q of H2P. So this we had already seen. So Q of H2P is nothing but this will be equal to IE times of this angle, that is cos of 30 degree into omega times of P2H into we will be having the area of the heater over here. So this area of heater we need to find, and omega P2H we need to find. So omega P2H, we already know that it is area of this object. From part to heater will be area of the part. To cos of, okay, so over here, since this is our heater and this is the radiating the energy, so I think this will be 60 degree over here, and this angle is 30 degree. So this is 30 degree upon the distance, that is L square. So theta 1 upon L square, that is what we have been given. So this we can calculate it as AP. We have been given as 0.007. Cos of 30 is I think √3/2 upon L square will be 9. (6.735) into 10⁻⁻⁴. Now we need to find the area of the heater from which this energy is radiated. So this AH will be 2 pi RH into W. So this RH is nothing but this radius of the heater. So if this is 30 degree, this is length of 3 meter. So this radius will come around L sine 30. No, L sine. So this is 60. Okay, so this is 60. So this will be 30. Yes. 2 pi L sine 30 into which is 30 mm. So this you can put over here. So have we been given IE? So we haven't been given IE, but IE we know that it is nothing but E upon pi cos of 60 is √3/2 omega pH. We saw it as 6.375 to 10⁻⁻⁴. AH will be 2 into pi into 3 width is 30 mm, that is 0.03. Now this total emissivity will be sigma T raised to 4, that is for a black hole. So this is basically EB upon pi, so it will be sigma sigma T raised to 4, that is 5.67 10 raised to minus 8. pH is 3000 Kelvin raised to 4. Cos of 60 is root 3 by 2 into, let's just calculate this term, 3 into 0.03, 6.735. So I think I have made some mistake over here. Let me just find the value of IE. IE is nothing but EB upon pi sigma TH raised to 4 upon pi. TH is 3000 raised to 4 into 5.67 raised to minus 8. 1. This will come around from 60 and then 10 raised to 3 meters square. Cos 60 will be 1 by 2. Correct. This is 1 by 2. So we saw this formula over here in the first question. See, if we have to find this, let's take this. If we have to find this, the radiation emitted from object 1 to object J, so you have to consider, you have to consider first this angle, that is the angle it makes with the perpendicular. So this is that is why we have considered in this question, I think 45. So this is the object. Let me just check. This is the heater. This is the perpendicular angle. What will be theta? I think I need to check this angle. This is a bit more confusing. So you are saying this should be 30, correct? Cos of 30. Correct. This is what is given. So because we are considering this as normal, so it will be 0 degree. This should be 0. I think the rest all angles I had taken this, correct. Correct. The normal to this surface will be this, and this is what the direction, that is what we are considering. So I think you are correct over here. It should be cos of 0. So this will come around 1. Then you can I think rest all part should be correct. So now what will be IE? We already calculated it as 1.462 into 10 raised to 6. Omega pH is, I think, 6.735 into 10 raised to minus 4. This area will be 3 divided by 2. So this entire area I have to calculate. So yes, this if you calculate it, it will come around 278.42 watt. So yes, the angle as you mentioned over here, it will be the angle of the radiation with respect to the perpendicular of the surface. So this is the surface and the perpendicular is basically this line. The radiation that we have been given in the question is also this line. So the angle is basically 0 degree, not 60 degree. So it's the final answer will come around 278.42 watt. So that is the final answer, 278.42 watt. So yes, we have been given that cos theta equal to, and that is the theta is 0 degree as we discussed. So that was all related to the previous week. I think I don't have any more questions. So again, if you have a few more doubts, you can ask me, or else we can end today's session. This slides, yes, we usually share it, so it should be available to you. Are you not able to see those? I think you are not able to see the recordings also. Are you able to see the recordings? Have they provided you with the links? Because earlier they used to just provide this link over here. Okay, so over here we have the recordings. Okay, so from this Excel sheet you can see. So this is my presentation folder link. So over here I will just upload today's lecture number 8 after this class, after around 9:15. Then you can see all the previous lectures are more or less I have provided over here. And the class recordings you can see from this YouTube links. So all those recordings are uploaded over here. So these slides I will make available. I think yes, we have heat exchanger, we have this LMTD also. Over here we don't have this heat exchanger. We don't have week 12, I think, in this session. In this session, we don't have week 12. Let me just confirm. Lecture number 55. So I don't think in heat transfer, in the current session, we don't have this heat transfer. But in the previous, yes, heat exchanger, correct, sorry, heat exchanger. But in the previous running of this course, sir had discussed this heat exchanger. Week 12 was heat exchanger. I'm not sure if they will put that forward, but I think it should be, heat exchanger should be available in the 12th week. Yes, if there is 12th week, then the 12th week will be heat exchanger. Then there will be heat exchanger. See, I can't, it should be available online. I can't promote this soft copy online, but I'm 100% sure that the copy is available online. It is available, that I'm 100% sure. All the class notes are uploaded in these books that has been discussed over here. Okay, so if you don't have any doubts, then I will be here until 9, so that if anyone else joins, so I will be around here, or else you can just leave the meeting. Yes. Fifth assignment, this assignment, correct? Do you have this one? Are you talking about this question? Assignment. Then it should be some other assignment. Which assignment? Fourth or in fifth? Are you talking about this question where we have to find the hmm, hmm. So you'll be having this solution, correct? So see, the ratio of the hydrodynamic and thermal boundary layer is given by this Prandtl number raised to n. And I think in the question you have been given that the Prandtl number is point, and then find that n equal to 0.355. For this given system, I think n should have been provided, that is 0.355. So I think n was not provided. No, but see over here. No, see over here they have calculated the value of n. From the given information, you can calculate the value of n and then find the value at different value of Prandtl number. So if the Prandtl number value was 0.709, then using that information, you can find the value of n is 0.355. And then for other fluid that is ethylene glycol, the Prandtl number is 211, and for that you can find that. These solutions are available to you, correct? All those solutions. Hmm. Hmm. Okay, thank you. I will be here until 8:50. If you want, you can leave. Hello. Hello. Hmm. Hmm. इसमें सबका वो भी है और मैप लेके जाना है उसके पास और ऐसा भी नहीं फाइव ग्रेड था 500 से प्रीमियम जैसे नहीं ले रहे हैं ऐसा इससे ले रहे हैं तो 500 से और प्रीमियम ले सकते हैं इसको इवन के जगह पे सादा ले सकता है मेरे लिखा है 500 से और प्रीमियम ले सकते हैं प्रीमियम प्रीमियम ले सकते हैं सादा ले सकते हैं और ये सो मैंने लिखा है पहले का ये सादा और कॉलम पे तो हाउ आई कैन जैसे नहीं तो फिर एक ही दिन में सब कर दो ना, तो ऐसा करना था कल पेमेंट, नहीं तो ऐसा तो कल खाली पेमेंट कर देना, तो बोलना कि अप्रोक्सीमेटली 420 वाला है, फाइनल में हम आपको बाद में एक हफ्ते पहले बता देंगे। हाँ हाँ, वो तो वैसे मुझको अगर एडवांस से तो लमसम भी देंगे ना आता पूरा। हाँ, ठीक है, वैसे तो आप पूरे लेके जाके ना बात कर लेंगे। और ऐसा करना अभी 20,000 तो आगे तुमको बता देंगे तो ये तो पीछ की क्योंकि मैं ऐसा करता हूँ फ्यूचर में अगर आइटम चेंज हो गए तो कॉस्ट चेंज हुआ इसके लिए आइटम आपने चेंज कर दिया और हो जाएगा। हाँ एकदम मोस्टली से बता दें कोई सब्जी का खाओ सब्जी साथ सब्जी है इसमें फ्राई हो जाएगा, फ्राई का जो हो जाता है। हाँ वैसे मतलब कि मैं आइटम उतना लिखा नहीं है फ्राई वाली आइटम, तो उनके तो इनको जाकर हाँ। हम्म, हम्म। और कितने अप्रोक्सीमेटली 120 का ही है ना। नहीं अभी मेरे वाले लिस्ट में मैंने तो बता दो उसमें ये 120 बाकी एक देता हूँ बाद में तो बना है। तो अभी एडवांस से जगह 120 के हिसाब से ही देने का है। हाँ क्योंकि देखो जब इसका क्या करवा देगा आई थिंक 5 किलो कम हो जाएंगे, तो लोअर से वाला भी पकड़ने का। हाँ वही फिर भी वन करता है। नहीं 7 से 9 मेरा पिछले को क्लास करता है इसके लिए,